Hey everybody, Dr. A here, and in this video we're going to be exploring another example of two-dimensional rigid body equilibrium. So before we get started, I just want to say thank you for being patient with me. I have a sore throat from allergies right now as I'm recording this video. I feel fine, so in case you were wondering, thanks for wondering. I feel fine. I just sound horrible. So thanks for your patience as we get through this example together. So let's go ahead and get started. In the given information, we're being asked to draw the free body diagram of the system and solve for the support reactions. So in this particular figure, we have what's called a cantilever beam, okay? A cantilever beam is a beam that is fixed, connected at one end, and it is free at the other end. So we see these very commonly with like building balconies. The beams that support a balcony of a building or maybe of an apartment are typically cantilever beams, okay? So again, fixed at one end and free at the opposite end. So it's just sticking straight out, okay? A flagpole is an example of like a vertical cantilever beam, which would be like sticking out of the ground, okay? So the length of this cantilever beam is 12 feet, and it has this, not uniform, it has a linearly increasing load along its length. So some people call this a triangular load, but really it's a linearly varying load. It starts at 0, and then it increases linearly throughout the length of the beam. At the far end of the beam, its high point is 0.1 KLF, or kips per linear foot. So let's go ahead and get started on the solution to this. First, we're going to draw the free body diagram. Now remember, whether or not a problem tells you to draw the free body, always do it. Just assume drawing the free body diagram is part of the problem, okay? And so to do this, we're going to draw our beam segment like this. Draw it a little bit better, okay? And we have this linearly varying load here. So this part looks, the same as the original figure. Here's that 0.1 KLF. There's the 12 feet. Now, what are the support reactions? Well, at the point A at the left, you have a fixed connection. So at fixed connections, there are 3 reactions that develop. There is a force in the x direction. We'll call that AX, or the horizontal direction. There is a force in the y direction. We'll call this AY. And then there is going to be a moment reaction, MA, okay? And the reason for that is because a fixed connection restrains all movement, okay? So we have that fixed connection preventing horizontal movement, vertical movement, and rotational movement. And remember, whenever a support is preventing movement, then it's going to develop some type of reaction, okay? So in this case, 2 forces and 1 moment reaction, okay? So do I know the direction of these? Not really, okay? We know that there is a horizontal reaction, a vertical reaction, and a moment reaction, but I am assuming the directions of these. I'm assuming AX is pointing to the right, I'm assuming AY is pointing up, and I'm assuming MA is pointing counterclockwise. And remember, we perform calculations, and if our reactions come out as positive values, that means that they are pointing in the direction we assumed. If they came out as negative values, that means that the reactions are pointing in the opposite direction that we assumed, okay? So let's go ahead and get started with this. I'm going to start with some of the forces in the x direction equals 0, and I look at everything happening in this free body diagram with an x component. The only force with an x component is AX, so here AX is just going to be 0. Okay, so that's one of my equilibrium equations. What about my other equilibrium equations? What else can I use here? Well, I can say some of the forces in the y direction equals 0 as well, and I can point things up as positive. So that's my second of 3 equilibrium equations to use here. So again, we look at everything with a vertical or a y component, okay? So AX is not coming into play here. MA is a rotation. It's not a force, okay? That's a moment. So MA does not come into play here. But what about AY? Well, I'm going to say positive AY. Now, what else has a vertical component? Well, this linearly varying load has a vertical component. In fact, it's pointing down, okay? So I'm going to say minus 1/2 times 0.1 KLF times 12 feet. And all that together, when I combine that together, is going to be equal to 0. How did I come up with this? Well, remember from our knowledge of distributed loads, whenever you have a distributed load, the equivalent force is the area of the load distribution. So this is a triangular shape. So I say 1/2 times one of the sides times the other side, and that gets me an equivalent point load, and that's going to be about right here, okay? F equiv. So that's what this term is. Now I'm going to do some rearranging, and I'm going to solve for AY. And so move this to the other side of the equation, say 0.5 times 0.1 times 12, and I get positive 0.6 kips, positive indicating pointing upwards, okay? Am I done? No, but almost. I'm going to say sum of the moments about point A equals 0. I'm going to call things going counterclockwise positive. Now, in this third and last equilibrium equation, I'm going to solve for MA. I'm going to solve for the reaction moment. Remember, this is a fixed connection here, so you have this reaction moment MA. So how do I solve for that? Well, I'm going to say MA, and I'm going to say that that's positive because I'm assuming MA is rotating counterclockwise in my free body diagram, which is a positive assumption. Then I'm going to say minus, and I'm going to compute the moment about point A due to this triangular load, okay? Now, that's going to be equal to that F equiv, which I already kind of sort of figured out, F equiv times what? Times a perpendicular distance, okay? Equals 0. And so if I write this out a little bit more clearly, that F equiv is really just this computation I did in my previous step. So I'm going to, here, let me write this out a little bit more clearly. I'm going to say MA minus 1/2 times 0.1 KLF times 12 feet. Okay, so that F equiv is this whole term right here. Now, what's the perpendicular distance? Well, remember from our knowledge of distributed loads, the perpendicular distance when you're dealing with a triangular shape is going to be equal to 2/3 of the length from the point of the triangle, okay? So that's going to be 2/3 of this entire 12-foot length. That's this perpendicular distance, okay, which is really 8 feet. So let's write that out completely so we understand the process. That's going to be times 2/3 times 12 feet equals 0. And again, this right here is my perpendicular distance, okay? And I'm going to punch through all of this together and move it to the other side of the equation. And when I do that, I'm going to be able to solve for MA, and let's see what we get. We get 0.5 times 0.1 times 12 times 2/3, also times 12. So I get 4.8 kip feet as my reaction. Now, it came out positive, which means that MA is in fact reacting in the direction I assumed in this free body diagram here, so counterclockwise, okay? It's reacting in a counterclockwise fashion because it came out positive. So finally, if I write a summary here, what will I have? I'll have AX is 0. AY, I believe, was 0.6 kips reacting upwards, and MA is 4.8 kip feet reacting counterclockwise. Okay. Now I encourage you to maybe pause the video, write all this out together, in your own, handwriting on your own paper, and do some unit management here. Okay. You should find that when you have kips per foot times feet and then times feet again, what do you get? You get kips times feet, which are the units of moment here. So even the units check out, okay? So that concludes this example. Thanks for being patient with me with my allergy-filled throat. Please don't forget to hit like and subscribe and be on the lookout for other content like this. Thanks again for watching.